Hello. When I was in primary school, I frequently remember my headmistress telling me to stop dithering. Well, always being the rebel, today we're going to be doing nothing but dithering whilst we explore the Floyd Steinberg dithering algorithm.
It wouldn't be wrong to say that dithering these days is a little bit anachronistic. It's an algorithm of yesteryear that has little purpose in modern society. That said, I think it's a very interesting algorithm, and has plenty of uses from visual stylization down to working with graphics on restricted systems such as embedded platforms. In this video we're going to look at this little application I've made which allows us to pan and zoom around a full high definition image, such as this beautiful picture of Riza in Norway. I spend my holidays there. I'm sure many of you will know that behind the scenes this image is constructed of pixels, and we can zoom right in and have a look at some pixels. We like pixels on this channel. And pixels in this case consists of 3 channels of 8-bit information, red, green and blue. Given that that's 3 bytes, and when you have a high resolution image such as this, you've got the resolution times those 3 bytes, you often require a lot of storage for the graphical information in this image. It also makes some assumptions that the display is capable of displaying such vibrant colours, and very often, despite the marketing blurb, they are not. In fact, arguably, there are far more colours represented in those 3 bytes of pixel data than the eye can actually see. So this raises the question, why bother storing all that information? Well, one option is to simply reduce the number of bits per pixel, and we can do that in this program. So if I press down the Q key, I've quantized the image. In this case, I've quantized it to 3 bits per channel per pixel. And you can see it gets these layers. We'll have a look. It approximates the image very well. But if we have a look at it closely, we can see that there are a limited number of colours in the available palette. When you're zoomed out and you squint your eyes a bit, it looks okay. But when you start to look at some of the detail, you start to see artifacts. So for example, we have banding here, where one shade is in high contrast to the next shade. Dithering aims to solve this problem. So here is the original image. Here is the quantized image, and if I press the W key, I can look at the overall dithered image. And hopefully it's apparent via all the YouTube compression why dithering is quite a useful strategy. Here are our bands, and here is the dithered equivalent. What's interesting about dithering is it's chosen only the same pixels that are available to it via the quantization. There's no additional colours introduced into this image. But dithering, and in particular the Floyd Steinberg algorithm, allows us to intelligently choose which pixels should become which colour, resulting in a far nicer approximation of the original image. So one last look, there's the original image, there's the dithered equivalent, and you can probably see it's very difficult to spot the difference. Yet whilst dithered, we only need 3 bits per channel per pixel. Just in case you need a more compelling example, I've reduced the number of bits to 2, and we'll look at this code later of course. With just 2 bits per pixel, we've only got 4 shades of red, 4 shades of blue and 4 shades of green combined to represent this image. If I look at the naively quantized image, we can start to see it looks pretty bad and everything's a bit grey and miserable. But if we look at the dithered equivalent, well, you can tell that it's definitely been dithered, but it's still not a bad approximation at all. Yet don't forget the key component is that the individual pixels have not generated new colours, we've just distributed that colour information more wisely.
I think the most remarkable thing about this algorithm is its simplicity.
In fact, as is often the case when starting with a new algorithm, we look at Wikipedia page, it provides the entire code for us, and there's barely any code at all. For me, this gives the algorithm a satisfaction score of 10, in that it achieves something quite wonderful with barely any code.
As usual on this channel, I'm going to be using my Pixel game engine to implement a small viewing application that will allow us to explore this algorithm. But also, as usual on this channel, you don't have to use the Pixel game engine at all. It just provides a way for me to conveniently draw pixels and handle user input. And like most of the videos on this channel, you can implement the code in other languages. However, it was whilst exploring this algorithm that I discovered that the peripheral C++ code around it is probably more interesting than the algorithm itself. So let's get started.
I'm starting with a bare bones Pixel game engine application. I've created a class called Dithering, which inherits from the Pixel Game Engine base class. It's important that you override two functions. OnUserCreate is called once at the start of your application, and OnUserUpdate is called every frame. In my main function, I'm creating an instance of my Dithering class, and I'm calling the construct function to set the resolution of the window that I want. And in this case, it's quite a high resolution window. It's 1280 pixels wide by 960 pixels tall, and each pixel has a ratio of 1 to each screen pixel. And then I start the game engine. Fundamentally, I'm going to need to load an image to work with, so I'm going to create a unique pointer to a sprite, which is a 2D array of pixels, and each pixel has 4 channels: red, green, blue, and alpha. I'm going to need to load data into that sprite from a file, and I only want to do that once, so in OnUserCreate, I'm going to construct my unique pointer to the sprite class and give it the parameter of a file name, and it'll go away and load that for me. Each frame of my application, I want to clear the screen to black to erase whatever was there the previous frame, and I'm simply going to draw the image to the screen with the drawSprite function. Let's take a quick look to make sure everything's set up properly. Very nice. We can see that the image is too large for the display window, but I'd like to ensure that I can go and view any part of the image. I need to add panning and zooming. In Pixel Game Engine land, we can achieve this by using a utility class called a transformed view. We've used transformed view now in a few videos, so this shouldn't be new to frequent viewers of the channel. The transformed view object will conveniently tidy up all of the transformations required to drawing things in a user manipulatable way. In OnUserUpdate, I need to tell the transform view to be responsive to the mouse buttons, and I can do that with this handle pan and zoom function. By default, it assumes that the middle mouse button is used for panning and zooming. And instead of just drawing the sprite to the screen directly, we now get the transformed view to draw the sprite instead. We just quickly test this, and we can see the image as before, but now if I hold the middle mouse button, I can drag the image, and as I scroll with the wheel, I can zoom in and out.
This is actually a nifty combination to explore all sorts of image processing algorithms.
Let's not forget that before we can do any dithering, we must quantize the image first. i.e., we must reduce the amount of information that is in that image. And the most accessible way forward to do that is to reduce the number of colours available to be drawn. So I've added in a second sprite called pQuantized, which will store this intermediate quantized image. Naturally, I'm also going to need a final image for the dithered output. I'm going to construct these new images based upon the source image size.
Whenever you are working with image processing, I would always recommend that you start in the Grayscale domain first. It's simply less information to worry about dealing with.
Given that our image will include colour information, we should convert this to Grayscale. There are several ways to do that. For example, you could just take the red channel. But there is a more accepted method, where we take a portion of each colour channel and add them together. I'm going to use some so-called modern C++ magic here to help me do these conversions. I'm going to start by creating a little lambda function, and this is a pattern you'll see me use quite a lot in this video. This lambda function takes in a pixel and will output a pixel. In this case, I'm going to take a proportion of the red channel, add a proportion of the green channel, and finally add a proportion of the blue channel. Unsurprisingly, these coefficients add up to 1. Now my pixel type doesn't support grayscale naturally, so what I'm going to do is take this grayscale value and simply write it to all of the red, green and blue channels of the pixel. This means when I draw it to the screen, it will look correct. I'm then going to use the standard transform function to convert each of the pixels in my source image into the grayscale equivalents, using the lambda function we've just created. Let's take a look. Very nice. We can see that the image has had its colours removed. To begin with, I'm going to quantize to 1 bit per pixel. That means if it is a light grey pixel in colour, then it goes white, and if it's a dark grey pixel in colour, it's going to go black. And I'm going to use a similar strategy. I'm going to create a little lambda function which takes an input pixel and outputs an output pixel, and that's purely based on one of the channels of the input pixel being less than 128. It outputs a black or a white equivalent pixel. I'm then going to use the standard transform function again. This time my source image is as before, but my destination image is the quantized output image, and I'm passing in my lambda function to perform that routine. This will be effectively a threshold of the image at the 50% mark. Since we now have different images to draw, I'm going to add in some sensitivity to key presses, Q and W, and draw the appropriate image. If neither key is pressed, I'm just going to draw the source image. Let's take a look. Here is the input image, and if I press the Q key, we should see it quantized to 1 bit per pixel. It gets thresholded. There we go. Very nice. The dithering routine itself is a little bit more complicated, so I'm not going to put this into a lambda function. I'm going to create a normal function for this. And to this function, I'm going to pass in a pointer to the source image, a pointer to the destination image, but the algorithm does need to know how to quantize a particular color. So I need to be able to pass in a quantizing lambda function. And to do that, I'm using the standard function template type. Since we only need to dither once, we can do all of this in onUserCreate. I'm going to pass in my source image, the destination image, and the quantizing lambda function.
With our simple and crude framework in place, it's now time to get to the crux of the video. How do we do the dithering?
Let's start by assuming we have an image. And that image consists of pixels, with our top left being 0, 0, the width along the x-axis and the height along the y-axis. Dithering is a scanline algorithm. That means we process each pixel one at a time. Once we reach the end of a row, we go down to the next one. This makes dithering a notoriously serial algorithm. It's quite difficult to parallelize, and that's because as we process this pixel, we're going to give information to our neighbouring pixels that we've not yet processed. So we can't process this pixel until this one has been, this one has been, and this one has been. Not being able to parallelize very well may be one of the reasons you don't see dithering very often in graphics today. Each pixel in this image is represented by a grayscale value, and I want to quantize to just black or white. So starting with the first pixel, I'm going to take my original pixel value of 0, and I'm going to work out what the closest match to my allowed colours is. In this case, I've only got black or white, which is 0 or 100 in this case. So my closest quantized pixel, QP, is also 0. In fact, if I just go and threshold the whole image, this is the result that I get. I'm basically checking, is a grayscale value greater than the halfway mark, 50%. If I calculate the error between my original pixel and my quantized pixel, I can see that that's also 0. Therefore, this first pixel has been perfectly matched. Let's move on to the next pixel. The original pixel value is 40, but the nearest quantized pixel I can have is still 0. Now I have an error of 40. There is brightness in this pixel, which is going to get lost because we're snapping to, well, black. It would be a shame to lose this brightness information, because it's clearly important to the spatial information in the image. And the point of Floyd Steinberg dithering is to distribute this error to the pixels we've not yet processed, because that brightness might influence how those pixels become quantized. And Floyd Steinberg dictates that we distribute that error in the following way. 7/16 of it goes right, 5/16 of it go down, 3/16 of it go to the bottom left, and 1/16 of it goes to the bottom right. There's an asymmetry here because as the algorithm is working from top left to bottom right, those bottom right pixels are going to see a lot more error diffused into them than the bottom left. Therefore, the coefficients are lower, and no surprises that these coefficients add up to 1. So 100% of the error is diffused to the neighbours that have not yet been processed. So 7/16 of 40 is approximately 18. So I'm going to change my grayscale value in this cell to the 40 it was originally plus the 18. So about 58. It's actually 17.5, but I want to keep it simple. 5/16 of the error going south changes this to 62, this one to 18, and this one to 33. So even though this pixel had brightness that has been lost by being quantized, that brightness has been diffused to the neighbours. That pixel is done, and we move on to the next. We can now see that the original grayscale value here that was 40 resulted in a quantized pixel of 0. But now, with the brightness information from the error diffused from the neighbour we've just processed, it will actually quantize towards white. In effect, the lost brightness from this pixel has illuminated its neighbour. So for this pixel, its original value was 58, the quantized pixel was 100, and so now our error is minus 42. In effect, we've now gone full circle. We're saying, well, hang on, this pixel has now contributed far too much brightness to this region of the image. So we need to distribute some darkness to our neighbours. 7/16 of minus 42 brings this pixel down to about 1. This one gets pulled down to about 55. This one gets pulled down to about 20. And this one is only slightly altered, becomes about 27. And really this is all there is to it. We do this for every single pixel in the image. The effect is that the areas with lots of brightness can diffuse into areas with lots of darkness, and vice versa. But rather than diffusing with a hard stop, which is what would happen if we just quantized the pixels, we allow the error to propagate that diffusion gracefully. This is one of those algorithms which is easier to just code than actually draw. So let's get on with it. First thing I'll do is copy over the source information into the destination image. That's because the destination image is going to contain all of those values that we need to modify. And I'll add 2 nested for loops that will allow us to scan through each column 1 row at a time. I'm going to grab the original pixel value from the image. And then I need to quantize that pixel based upon our chosen quantization function. So far so good, but now we hit our first peculiarity. If we have a look at the Pixel Game Engine pixel type, and have a look at any of the operators, what we can see is that the Pixel Game Engine makes every effort to naturally clamp the values to 0 and 255. This is typically what you would want out of the Pixel Game Engine. However, we need to allow our error to become negative. This means I can't just simply store the difference between OP and QP as another pixel. And I'm also going to make an assumption that we'll do this for all 3 channels independently. That way, when we scale this back up to working with colour images, we don't need to change anything. There is nothing clever about the difference between full colour and grayscale images. Just full colour, you have to do everything 3 times. There's no sort of cross-channel interdependence here. Once I've calculated the errors, I can simply set the destination's image pixel to that of our quantized pixel value. But I need to add to the destination neighbouring pixels the error distribution. And to do that, I'm going to create a little lambda function again called updatePixel. This lambda function captures the pixel's location, the destination image, and the error array we've just created. It takes in an offset that describes the relationship between this pixel and the pixel we're currently processing, and the actual error value to distribute to that pixel. We'll populate this lambda function in a minute, but just so you can understand its place, here I am calling it 4 times for the neighbours we've not yet processed, and you can see the coefficients from the Floyd Steinberg algorithm. So to update the pixel, I'm going to grab the pixel from the destination image, plus the offset this time. So this is getting one of the neighbouring pixels to the pixel we're working on. Because I need to work with the signed type, I'm going to convert the individual pixel channels, which are 8-bit unsigned bytes, into integers. I'm then going to distribute the error for each channel by adding it to the neighbouring pixel values. Finally, I'm going to write those new pixel values back out to the source image. But as I do so, I'm going to be careful of one thing. I'm going to use the standard clamp function to make sure that the value lies within the range of an unsigned byte. So that's setting the red channel, the green channel, and the blue channel. Now you might think, why do I have to do this clamping? Well, let's say I just allowed the integer 32 to truncate to the unsigned integer 8. If the integer value, say, was 270, then it would wrap around, and I don't want that to occur. And so to recap, we've created a function called Floyd Steinberg that takes the source and the destination image and some method of quantizing a particular colour. We populate the destination image with the source image to give all the pixels a starting value. Then we iterate through all of the pixels in a scanline fashion, testing them against the quantized equivalent pixel for that location. Whatever error there is between the quantized pixel and the original pixel, we distribute to the neighbours. And that is it. Very simple. Let's take a look. Here's our original image. Here's our thresholded image, which is, well, the same as quantizing to 1 bit. And here is our dithered image. And we can start to see that the shading is working quite nicely. Now, one of the problems you're going to get when you do transformed view is you get noise like this, and that's because we're now sampling the dithered image, so it's not going to look quite right. So always ensure when you're viewing the dithered image that you're actually sort of zoomed in a little bit. And we can see that the dithering works really well at capturing the shading. The darker areas are on the whole darker than the lighter areas. It's very nice, and it's a far smarter choice of thresholding than this. Having a framework like this now makes it very easy to change things and experiment. So let's say I didn't want to just quantize grayscale to 1 bit, I wanted to quantize it to, well, a selection of bits. I could come up with a way of masking the bits, basically taking the most significant bits out of each pixel value. But instead, I'm going to try and do this mathematically. If I've got 2 bits, I've got 4 levels. In this case, indexed 0, 1, 2 and 3. Since I know that my grayscale input image has the same value in the red, green and blue channels, I'm only interested in looking at the red channel. So I'm going to take the red channel value and divide it by the maximum pixel value. This will give me a value between 0 and 1. And I multiply that by the number of levels that I've got, and I round that down to the nearest integer. Actually, it could also round it up, I suppose. Once I know the closest level, I can then normalize it with respect to the number of levels and scale it back up to the actual colour value between 0 and 255. And just for good measure, just in case something starts to go a bit weird, I've thrown in a clamp as well, probably unnecessary. And finally, the lambda function can return a pixel made of the new quantized colour. So now I can tell my algorithms to use this different method of quantization. With 2 bits, we know that there should be 4 shades of grey. Let's have a look. There's the original image, and here is the naively quantized image. And indeed, we can see we've got black, and dark grey, and light grey, and white. We have just got 4 shades of grey. And if I look at the quantized equivalent, again, we'll only ever have 4 shades of grey, but the distribution is far more pleasing. If I change this to 3 bits, we should have 8 shades of grey per pixel. Let's have a look at what the image quality looks like now. And I've got a feeling that the YouTube video compression is not going to allow me to sort of convey this very nicely, but I'll try. So here's the original image, and here is the quantized naively approach. It looks okay, to be fair. And here is the dithered approach. So the original image and the dithered image start to look very similar. You do start to see some noise in the dark areas, and that's because the Floyd Steinberg algorithm has a tendency to illuminate. It propagates brightness, and because the pixels get clamped, it's very difficult for it to propagate darkness. Still, it works quite well. We can take this grayscale approach of quantization and just extend it across 3 channels to give us the same but for RGB. So let's take a look at that. I'm going to pass in this RGB quantization function to both of my algorithms. Now, one of the things I'll need to do is not convert to grayscale. I'm now working with the colour images. Colour images with 4 shades of red, 4 shades of green and 4 shades of blue. There's the original image. There's our naive quantization. And there's our diffused quantization. I think that's quite nice. And let's say I go to 4 bits per pixel here. So this is 16 shades of red, green and blue per pixel. Original image. Very difficult to actually see now that the naive quantization is actually doing anything at all. I reckon that probably won't come through in the video compression. But if we have a look at this area here, we can see definite banding going on. So there's the banding and there is the diffused image. So the diffused image, well, certainly to my old eyes through these glasses, which are covered in smudges, it's starting to look very difficult to see any difference. Yet we've halved the information requirements to store this image. Quantizing colours is a topic all in itself. Here I've created a lambda function where I specify manually what colours are allowed in my palette. Given an input pixel, I can estimate how close it is to one of those colours. It's a bit slow because I have to test them all to see which one is the closest, but I'm effectively looking for the Pythagorean distance between the input colour and my palette colour, and looking for the shortest distance as well. When we restrict the palette in this way, we can start to see one of the interesting properties of the algorithm. In fact, it's probably my favourite property. Here is the original image, and my palette only consists of black, white, and the 6 primary and secondary colours. If we look at the quantized map, we can see it looks terrible, really bad. It's as if the saturation has been dialed up to the max. And if we look at the dithered map, we can still see, well, it looks quite terrible. But do you know what? It's not done so bad. Yes, you have to squint your eyes a little bit, but it's starting to somewhat reflect the original image. And we can see that it only consists of the colours we've allowed out of that palette. In fact, let's give it even more of a challenge. I'm going to remove red, green and blue from the available colours it's allowed to construct images out of. I'm just going to have black, white, yellow, magenta and cyan. Here's the original. Here is the quantized map, which really doesn't look very good at all now. And here is the diffused mapping. Now it still doesn't look great, but again it's not done so bad at all. We've not even included red as one of the colours. Yet we can distinctly see red, we can see shades of dark blue, we can see that the yellow, there's light yellows and there's dark yellows. It's a visual optical trick, of course, but it's a very compelling one. We can see all of the information that's in the forest in the background. If we go back to the other map, a lot of that just gets lost. We can see that the boats are distinctly different colours. Yes, of course they're not, because we've restricted everything to just 5 colours.
And I think that's one of the reasons I enjoy this algorithm so much. Like myself, it tries to do the best it can with what it's got. And I suppose my headmistress was right, there is a bit of dithering in me after all. As always, the source code for this video will be available on the GitHub. If you've enjoyed this video, a big thumbs up please. Come and have a chat on the Discord server, have a think about subscribing, and I'll see you next time. Take care.